Something is blocking the light from a distant star. It's not a planet, it's not another star. It's big, it's weird, and it doesn't follow any of the rules we know. For a while, some of the smartest people on the planet had to seriously consider an idea that sounds like it came straight from a science fiction novel. They had to ask, are we seeing an alien megastructure? The story starts with the Space Telescope, NASA's Kepler mission. Its job was simple, but huge. It stared at one patch of sky for years. It watched about 150,000 stars, all at once. It was looking for tiny, regular dips in starlight. Those dips usually mean a planet is passing in front of its star. It's like a fly buzzing in front of a distant searchlight. You don't see the fly, but you see the light dim just a little. Kepler found thousands of planets this way. It changed how we see the universe. It showed us that planets are everywhere, but the Kepler telescope gathered too much data for professional astronomers to sort through alone. There was just too much of it. So they started a project called Planet Hunters. It was a citizen science project. Anyone, anywhere, with a computer and an internet connection could help. They could look at the graphs of starlight, the light curves, and flag anything that looked interesting. People are good at pattern recognition, sometimes better than computers. In 2011, a few of these citizen scientists noticed something strange. They were looking at a star called KIC 8,462,852. It was a pretty normal-looking star, a little bigger and hotter than our sun, about 1,500 light-years away. But its light curve was anything but normal. A typical planet like Jupiter passing in front of a star like this would block maybe 1% of its light. And it would do it on a regular schedule in orbit. This star was different. The light from KIC 8,462,852 was dipping by huge amounts. Not 1%, but 15%, sometimes 22%. That's a massive drop. To block that much light, whatever was passing in front of it had to be gigantic. And the dips weren't regular. They didn't happen on a neat, predictable schedule. They were chaotic. They would last for days, or even a week. There wasn't a single clean dip. It was a whole series of jagged, messy drops in brightness. It looked like a whole swarm of stuff was passing in front of the star. The planet hunters flagged it. The professional astronomers saw it. They were confused. Tabetha Boyajian, an astronomer at Yale, led the team that investigated. The star eventually became known as Tabby's star in her honor. Her team looked at the data carefully. They checked everything. Maybe it was a mistake. Maybe the telescope was acting up. Maybe there was a problem with the data processing. Yes, they checked it all. The data was real. The star was really dimming in this bizarre way. So the search for an explanation began. They had to start with the normal stuff. The natural explanations. The first idea was a huge cloud of dust and rock. Maybe a bunch of planets had just collided. A planetary smash-up would create a massive debris field. This field could orbit the star and block its light. It's a plausible idea. It happens. But there's a problem. A collision like that creates a lot of fine dust. And when that dust is near a star, it gets warm. Warm dust glows in infrared light. So if there was a debris cloud, we should see a strong infrared signal coming from the star. They looked. There was no extra infrared glow. That explanation didn't fit. What about comets? Maybe a giant swarm of comets was passing in front of the star. A single comet wouldn't be enough. Not even close. You would need hundreds, maybe thousands of massive comets all bunched together to explain the light dips. It's what they called a family of comets. This became the leading natural explanation for a while. It could explain the irregular dips. Comets have tails of gas and dust that could create the messy light curve. And since comets are mostly ice, they wouldn't get as warm as a rock field. So the lack of infrared light was less of a problem. But the comet idea had its own issues. First, the sheer number of comets required was staggering. It would have to be an event of a scale we've never imagined. Something would have had to disturb this massive cloud of comets, maybe a passing star, and send them all falling in toward their sun at the same time. The timing would have to be perfect for us to be watching right when it happened. It seemed unlikely. It was a stretch. But the universe is a big place. Unlikely things happen. While this debate was going on, something else was discovered. An astronomer named Bradley Schaefer decided to look at old data. He went back and looked at photographic plates of the sky from the past century. He wanted to see what Tabby's star had been doing over the long term. What he found made the mystery even deeper. The star wasn't just dipping erratically for a few days at a time. It seemed to be getting fainter over the course of the whole century. It had dimmed by about 20% since the 1890s. This was a huge problem for the comet theory. A swarm of comets is a temporary event. It passes by. It doesn't cause a star to slowly and steadily fade for 100 years. This long-term dimming was a completely different phenomenon from the short-term jagged dips. Now, there were two bizarre things to explain, not just one. Other researchers reanalyzed the old data and debated Schaefer's findings. Some thought the old photographic plates weren't reliable enough, but then data from the Kepler mission itself showed the star had also dimmed by about 3% over the 4 years it was being watched. This wasn't a sudden dip, it was a slow, gradual fade. The long-term dimming seemed to be real. So the natural explanations were all in trouble. A planetary collision didn't fit the infrared data. A giant swarm of comets didn't explain the century-long fading. Other ideas were thrown around too. Maybe the star itself was weird. Maybe it had some strange internal process that made its brightness flicker. But Tabby's star is an F-type star. They are generally very stable. They're not supposed to do this. Maybe it was a cloud of dust in interstellar space, just sitting between us and the star. But if that were the case, it should affect the nearby stars as well, and it didn't. All the neighboring stars looked perfectly normal. Every natural explanation they came up with had a serious flaw. It didn't fit all the evidence. Scientists were stuck. And when you're stuck, when all the usual answers fail, you have to start considering the unusual ones. This is where the idea of an alien megastructure came in. It was proposed by an astronomer named Jason Wright. He and his colleagues looked at the data and pointed out that it was consistent with something we've never seen before. Something artificial, specifically a Dyson Swarm. The idea of a Dyson sphere comes from a physicist named Freeman Dyson. He thought about what a truly advanced ancient civilization would need. The answer is energy. A civilization's energy needs to grow over time. Eventually, they might need to capture a significant fraction of the energy from their home star. A star puts out an enormous amount of power. Our planet only catches a tiny, tiny fraction of it. So how do you capture all that energy? You build structures around the star. A full, solid shell is probably impossible. It would have huge gravitational and structural problems, but a swarm is more plausible. You could build a vast collection of orbiting structures. Maybe they're giant solar collectors. Maybe they're habitats, billions of them. They would all orbit the star, collecting its energy. Now, from a distance, this swarm of objects would look like a cloud that blocks the star's light. How would a Dyson swarm look to our telescopes? Well, it would block a lot of light. The dips wouldn't be small and neat like a planet. They would be big and messy, depending on how the swarm was constructed and how dense the different parts were. The dips would be irregular, as different clumps of structures moved into our line of sight. This matched the Kepler data perfectly. It explained the huge, chaotic drops in brightness. What about the lack of infrared heat? A Dyson swarm would have to radiate waste heat. It's a basic law of physics. Any energy you use has to go somewhere. The structures would get warm and glow in the infrared, but they would be designed to be efficient. They might radiate heat at a much cooler temperature than a simple cloud of hot dust. So the lack of a strong, hot infrared signal wasn't necessarily a deal breaker for the alien megastructure idea. It could still fit. And what about the long-term dimming? The century-long fade? That could be explained too. It could be the sign of a construction project. We could be watching a civilization in the process of building its swarm. Every year they add more structures, more collectors, and the star gets a little bit fainter from our perspective. It was a wild idea. It was also a testable one. The Search for Extraterrestrial Intelligence, or SETI, had traditionally listened for radio signals. But this was a different approach, looking for a technosignature, a sign of technology so vast, it changes the appearance of a star. The SETI Institute pointed its radio telescopes at Tabby's star. They listened, they heard nothing. No obvious narrow-band signals that would indicate communication or technology. That was a point against the alien idea, but not a fatal one. Maybe they don't use radio. Maybe they communicate with lasers, or maybe they just aren't trying to talk to us at all. The idea of an alien megastructure around Tabby's star captured the public imagination. It was everywhere. It was an exciting, incredible possibility. For scientists, it wasn't about belief. It was a hypothesis, an explanation that fit the known facts better than many of the natural ones. But science requires extraordinary evidence for extraordinary claims. The work was just beginning. Tabetha Boyajian and her team needed more data. The Kepler telescope wasn't watching the star anymore. To understand what was happening, they needed to be able to watch it continuously with many different kinds of telescopes on the ground. When the next big dimming event happened, they wanted to be ready to observe it in every wavelength of light imaginable. This kind of telescope time is expensive and hard to get, so she did something unusual. She and her team launched a Kickstarter campaign. They asked the public for help. The response was huge. People were fascinated by the mystery. They raised over $100,000 to buy telescope time. They got their network of telescopes ready, and they waited. In May of 2017, it happened. The star started to dim again. The alerts went out. Astronomers all over the world pointed their instruments at Tabby's star. They collected a flood of new data. This was the crucial test. They were finally watching a dip in real time, with equipment that could analyze the light in detail. What they found was the key to the puzzle. They looked at how the star's light was being blocked across different colors, different wavelengths. If the object blocking the light was solid and opaque, like a planet or a giant alien solar panel, it would block all colors of light equally. Red light, blue light, green light, they would all dim by the same amount, but that's not what they saw. The new data showed that blue light was being blocked more than red light. This is a very specific signature. It's the signature of dust, not giant solid objects, but tiny particles. Think about a sunset on Earth. The sun looks red because our atmosphere scatters the blue light away, letting the red light pass through more easily. The same principle applies here. Whatever was passing in front of Tabby's star was made of particles small enough to scatter blue light more effectively than red light. It was dust. This was a major blow to the alien megastructure hypothesis. Giant, solid engineering projects wouldn't do this. But a cloud of fine dust particles would. The evidence was now pointing strongly away from aliens and back toward a natural, if still very strange, explanation. So if it's dust, where did it come from? And what about all the problems with the earlier dust and comet theories? The new data helped refine the picture. It's not interstellar dust floating between stars. It has to be circumstellar dust, meaning it's orbiting the star itself. It's part of that star system. The leading explanation today is some form of this dust theory. It's still not completely settled, but the picture is getting clearer. The dust is probably not from a planetary collision because the infrared heat is still missing. And it's probably not a simple swarm of comets. The truth might be something in between or something more complex. One idea is that we are seeing a single, massive exocomet, a comet in another solar system that is breaking apart as it orbits the star. Or maybe a planet with rings, like Saturn, but with a huge unstable ring system that is clumpy and uneven. Another possibility is that the star itself is responsible. Maybe it recently swallowed a planet or a large asteroid, and the material we're seeing is the leftover debris from that meal. What about the long-term dimming? The century-long fate is still a puzzle. Some scientists think it might be real, and could be caused by a gradual thickening of this dust cloud. Others think it might be an error in the old data, or a result of changes in telescope technology over the years. The more recent, reliable dimming seen by Kepler is also likely caused by this dust. It's not that the star itself is getting weaker, it's that our view of it is being increasingly obscured by a cloud of fine particles. So, the most likely answer to the mystery of Tabby's star is dust. It's a less exciting answer than a Dyson Swarm. There's a bit of disappointment in that. The universe is full of dust. It's a common thing. But the situation at Tabby's star is anything but common. The sheer amount of dust required to block 22% of a star's light is immense. It's more dust than we have in our entire solar system, all concentrated in one place. And the way it behaves, with its sudden deep dips, is unlike anything we've ever seen. Even if the answer isn't aliens, Tabby's star is still incredibly important. It taught us a lot. It showed us that the universe is still capable of completely surprising us. We thought we had a good handle on how stars behave. This one showed us we were wrong. There are processes out there we don't understand yet. It also changed the way we search for extraterrestrial intelligence. The idea of looking for technosignatures for the large-scale engineering of an advanced civilization is now a serious part of the search. Tabby's star was like a fire drill. It made scientists think about what a real signal might look like and how we would go about confirming it. What kind of data would we need? What follow-up observations would be necessary? If another, even more compelling candidate comes along, we'll be much better prepared. And it was a fantastic story of citizen science. It was ordinary people looking at data in their spare time who made this incredible discovery. It shows that anyone can contribute to our understanding of the cosmos. The mystery brought scientists and the public together, all focused on this one strange star in the sky. In the end, could an alien megastructure be blocking a star's light? The answer is yes, it could. In theory, it's a possibility. But is that what's happening at Tabby's star? Almost certainly not. The evidence we have now points to dust. A very strange, very mysterious cloud of dust, but dust all the same. Science follows the evidence, and the evidence doesn't support the alien hypothesis. Well, but the story isn't over. The star is still being watched. The mystery isn't completely solved. We know it's probably dust, but we don't know for sure where it came from or why it's behaving the way it is. It's a reminder that even the boring answers in space are often more complex and wonderful than we can imagine. And it leaves the big question hanging in the air. We looked at one star out of hundreds of billions and found something that baffled us for years. What else is out there waiting to be found? The search continues, and maybe, just maybe, the next strange signal won't be from a cloud of dust.